Hi, so the purpose of this video is to quickly showcase some preliminary image analysis techniques in QuPath, specifically how to perform cell counting. Um, this is a common, request in a lot of image analysis workflows to segment cells, quantify the number of cells, and quantify the number of subcategories of cells. So for this project, I'll be using one of the sample HistoWiz images, as well as a project that I've created in the previous tutorial. If you know how to create a QuPath project and you know how to load in images, there's no need to see the previous video. But if that's needed, feel free to send me an email at mark@histwiz.com and I will send you a copy of the video. All right, so let's begin. First thing we want to do is to locate and open our QuPath project. It's located right here. Seeing as we will most likely want to quantify cells that are positive for one marker, I will operate on a brown stained image, but the methodology can be applicable to H&E stained sections, and even simpler is with analyzing fluorescence microscopy data. So let's quickly just wipe everything. I have some annotations here, but let's just start fresh. We can select all annotations and delete all selected objects. So now we have nothing but just a loaded image. Next up, we want to specify the color vectors. What this means is we want to teach the QuPath program what pure hematoxylin look like, what pure dab stain look like, and what background looks like. If you're working with an H&E section, methodology will be the same, but instead of dab, we'll be using eosin. To do this, load in your image, create a small rectangular annotation, go to Analyze, Preprocessing, Estimate Stain Vectors, and you can press Yes. Click Auto. Even if you're working with an H&E image, this is completely optional, but I don't think this actually gives much of a benefit. You can click OK, OK again, and within a matter of seconds, it should have been automatically computing what pure hematoxylin looks like, what pure dab looks like. Um, Not too satisfied with how that looks, so I'll give it another shot. This time we'll take a slightly larger area. Maybe over here, for example. We want the area to have plenty of white space. And try that again. Estimate stain vectors. Yes. Auto. Okay. Okay. And all right. I guess this is as good of a job as we can get. All right. So now that we have specified our color vectors, we can delete this annotation. For convenience sake, and in terms of reproducibility, because I want you, the client, to be able to do this without much of a hassle, I will turn on this little input display. So anytime I do a left click, a right click, whatever, it'll show up, here. Even Control S, like if I wanted to save an image. So, let me put this off screen, but the client request that I was doing this for is order number 16998. We would want to count cells in QuPath. All right, let's get started. So right off the bat, this can be a computationally intensive task, especially when you have an image that is almost 2 centimeters in diameter, which has 109,000 pixels. So yes, this can become fairly computationally intensive. So anytime we do parameter optimization for what thresholds or hyperparameter settings we want to use for the cell segmentation algorithm, it's best to start small, see how it works, and then gradually apply it to a larger image. So first off, let's find a nice representative area to analyze. Here, if the end goal is segmenting this entire area, we can start off with a very small subset right here. Now we want to first run cell detection. There's many different parameters you can use to optimize the accuracy of cell detection. I would say that you, as the client, should feel free to try around with all of these different parameters and see what they do, get a good sense of how they can improve the accuracy of cell segmentation. But always try it out in a small area because some of these can get rather computationally intensive. First being is detection image. What part of the image, or rather what color transform should we use before we perform cell segmentation? You can either use hematoxylin by itself or the sum of hematoxylin and all other colors. So if we do hematoxylin alone, the image that it'll be operating on looks something like this. This is the grayscale equivalent of hematoxylin, and it'll attempt to detect cells here. We can do optical density sum, which is the sum of hematoxylin and DAB. There isn't one, right answer as to what is best, but it's more so trial and error. Anyways, for now, let's stick with hematoxylin. 5 micron resolution. It's a slightly lower resolution than what the image was acquired at, and it just basically means that it'll downsample the image. Downsampling reduces accuracy but improves performance drastically. If you wanted to disable downsampling, you simply set this value to 0, or whatever the image resolution is. There's several other parameters, and for now I wouldn't worry about it too much. Minimum area and maximum area denote what is the minimum size of nuclei we want to include, and the maximum size of nuclei we want to include. Anything outside these ranges will be deleted. This one parameter here is arguably the one that you will be spending the most time, and it's the threshold on this detection image that we want to use for cell detection. Lower values indicate more objects are going to be detected. Higher values mean fewer objects are going to be detected. And on that note, let's keep everything else the same. And we click run. So you can see it, as a first pass, it does, somewhat of a reasonable job. The problem here is that it's detecting some of these intense brown areas as being hematoxylin positive. So what we can do is we can raise the threshold to maybe 0.2. And this should, in theory, detect fewer cells, which it has, but now we're starting to miss some of the hematoxylin positive cells. There isn't any, right parameter because it can differ greatly in terms of your images. What's important is keeping it consistent. So if you run cell detection on one image, make sure you use the exact same parameters on any subsequent image or area. The way you can do this is anytime you click the run button, they'll save a log of it here. So this has all of the parameters that were last used. And if you want to quickly, get these parameters out, you can click create script, which creates a script containing every single command you've ever done. And you can simply delete everything except for the most recent version of the specific function. So for example, the set color to convolution stains was used to define what our pure brown stain is and what pure hematoxylin stain is. So we can delete those. And this is the plugin for cell detection. We can delete everything else here because these are not relevant. And on that note, if we click run, we should get identical segmentations, which we have. Now, I'm not going to show in the case of this video on how to tune these parameters because there is no right way, but you can basically play around with each and every one of these values until you get a segmentation that, encapsulates or is able to detect all of the cells that you want to ultimately quantify. Once we're satisfied with the parameters, we can delete this annotation. Click no because we want to delete everything, basically start fresh. And then we can create an annotation encompassing this entire tissue. There are ways to automate this process, but if you aren't working with hundreds of slides, it'll take just a matter of seconds to draw an outline for this tissue. And so you click the wand tool and you just quickly brush over this with its nice little edge detection parameters or edge detection algorithm, whatever you want to call it. And now we have our tissue of interest. Some people worry about, oh, we're messing up these important little edge cases, but generally speaking, I don't like to include too much tissue on the edge because of edge artifacts relating to how the sectioning can lead to, some artifacts basically. For example, we'll have, really intense staining here, which can mistakenly cause a cell detection to be erroneously detected in this border. All in all, the total amount of tissue being missed out on compared to the large body of tissue is negligible. Choosing to include this border or not will make no difference whatsoever. In some cases, though, you might have a fold large enough to make an impact on your data. This fold over here doesn't, but I will still show you how to exclude this from analysis. All you have to do is make sure that your tissue is still selected, which it is based on the yellow outline. Hold down the Alt key if you're on a Windows computer, and start dragging outside of the box until you kind of clear out some of this area inside of here. Again, there's no point in doing such a minor modification, but I wanted to show how you can modify these kinds of annotations in terms of whole slide image analysis. Next, what we might want to do is, perform separate analyses in different subregions of this tissue. So let's pretend we want to treat this structure, whatever you want to call the structure, as a different annotation class. The way we could go about this is, by deleting this from the current annotation. And again, use the Alt key. This time I chose the wand tool instead of the brush tool. And yeah, we can just delete this annotation, delete this area as well, delete these areas, delete this, and delete this, as well as this. I'm not gonna, really fine tune this, again, just for the sake of demonstration, but there are many ways to get a more accurate tissue level, segmentation. Now, if we fill these annotations in with Shift F, we can see that this is not being classified as anything, but ultimately we want to classify both this outside tissue area and the inside tissue area as two separate classes. So I'm going to reset this to the default classes. We'll call this tumor, and now we need to start painting the inside tissue areas as a different class, stroma. It's probably not accurate even in the slightest, but again, for the sake of the demonstration, I'm just quickly showcasing some image analysis techniques. We press auto set, which now means that all new annotations are going to be assigned to the stroma class, and we used the, you can use either the brush tool or the wand tool. I'll use the brush tool and just kind of quickly squiggle all over here. But, so now it snaps in almost perfectly. How did I do this? If you start painting outside of an annotation, and you paint all over this, completely reckless, but just to make sure you cover all of the areas that we haven't classified as anything. If you hold Control Shift, and perform the slightest movement, it'll attempt to snap, basically. There we go. Snap inside. Let me just clear out this little fragment over here. And now you can see we have two stromal areas. Because we don't want to, analyze them separately, I'll merge these two annotations into one. So we select them both, right click, right click over here, edit multiple, merge selected. So now we have one tumor area and one stromal area. Now we want to run our cell segmentation parameters that we've already tuned, but in both of these areas. So again, hold down the control key or however you want to select these areas. Make sure both are selected as evident by the yellow outline, and click Run. You can see that it's starting to detect nuclei. Depending on your computational resources at hand, this might take longer or shorter. Most likely longer. All the more reason to solicit HistoWiz's image analysis services. And as you can see, we have now segmented all of the cells in both of these areas. For simplicity, I will just show the boundaries of the cells. Now to answer the client request of client 16998, or at the order number 16998, the number of cells can be viewed in either of these annotations just by clicking on it. Number of detections is the number of cells. But the total number of cells by itself usually doesn't mean anything important. Larger areas, of course, will have more cells. If we're working with DAB stained images, or if we're trying to segment a specific cell subtype on H&E stained images, like lymphocytes or megakaryocytes or whatever you can view on an H&E image, we'd want to perform some kind of cell classification. The way we perform cell classification is by going to Classify, Object Classification, Create Single Measurement Classifier. Detections are all. We want to perform classification using DAB staining in the cytoplasm, maybe, or even whole cell, why not? Above threshold, we will call it positive. Below threshold, we'll call it negative. Turn on live preview, and you can see anything that is being classified as positive is now this kind of magenta color. Anything that is being classified as negative is... anything that is positive is red. Anything that is negative is this magenta color. You can tune what the exact threshold is, and again, this depends on whatever it is you consider to be positive for true positive staining. There isn't any right answer, and it might even differ drastically depending on the pathologist setting this threshold. But yeah, for any clinical related work, it's always good to get a pathologist feedback on it, as they're generally considered the gold standard. And again, all the more reason to solicit HistoWiz's services, because they have a dedicated team of pathologists working 24/7, specializing in a variety of cell subtypes, or a variety of tissue types. So once we're satisfied with whatever threshold it is we set, we click Apply. Happens almost instantaneously, even with a slow computer. And now when we click on these annotations, it'll tell us the percentage of cells positive for this marker. Ultimately, that is what we want to export. The way we export is we go to Measure, Export Measurements, click on the... we forgot something important. Save. Control S. Always important to save before we export the measurements. We click on the section we've just analyzed. This is 2286 control. Export type is annotation. This will mean that we'll have one row per annotation we've created in this image. If you don't have annotations, or if you don't have multiple annotations, you can use either the annotation or image tab. Again, up to you. Export type should be comma separated value. and choose where you want to export it. By default, it'll export in the project-based directory. Click Save, click Export, done. And now we go back to the project-based directory. Here we have the measurements, and hopefully this will answer all of the questions you have, Bernardo. And if not, I'm always happy to help develop a little bit more of a specialized workflow for you guys. But yep, you can now quantify for every image and for every region within that image the number of cells total, number of negative cells, number of positive cells, percentage of cells positive, number of positive cells per square millimeter, equivalent to cell density, and many other features. So ultimately, this is what you'd actually perform downstream statistical analysis on if you wanted to, say, determine whether or not there is a difference in cell counts in an experimental versus control group. The reason why I didn't want to just leave it at cell counts by itself is because cell counts are not normalized to anything. Larger tissue will have more cells, including more positive cells. By normalizing to the total number of cells, that percent positive score is no longer being biased by the number of cells in any given case. And yeah, I hope my screen was recording because I do not see an outline. Ah, perfect, it was. So on that note, without taking up too much of your time, I hope this tutorial was useful. If you have any questions, comments, or concerns, feel free to reach out to me at mark@hiswiz.com or contact any of your representative pathologists or anyone else involved in the team, and they can connect you with me. Yeah, so yeah, if you have any questions, comments, or concerns, feel free to reach out to me. I believe I have answered everything that there is to answer, but if not, feel free to schedule a meeting with me. All right, take care, and thank you for choosing HistoWiz.